everyone, in this video we are going to learn how to construct the hash diagram. Basically, hash diagram is a graphical representation of the Poset and it is different from the directed graph of a relation. So here we will first learn how to convert the directed graph of the relation into the equivalent hash diagram, and after that we will directly learn how to construct the hash diagram without constructing the directed graph. Suppose we have the directed graph. From directed graph, we can move to the hash diagram by taking these three steps. The first step is remove the self loops. As we know that Poset is a reflexive, so there is no need to add the loops in that case. Second case is eliminate all the edges that implies the transitive property. Transitive property means if A is related to B and B is related to C, means A is related to C, and if we have such edge, we need to remove that one. And third case is remove the direction from the edges and arrange the elements in an upward direction. How to arrange the element in an upward direction? Simply, if we have A is related with B, means if A has a relation with B element, rather than writing in this form, first we can place the vertex A in the bottom and the vertex B is placed above to the vertex A. By using these steps with each and every element, we will get the hash diagram. For example, in this case, we have taken the set A that contains the three elements 2, 4, 7. We need to draw the directed graph and the hash diagram with respect to this relation. We have already learned in the previous video that the set of integer with less than equal to relation is a poset. So there is no need to figure out whether this is a poset or a not. Directly we will move to the directed graph. But before that, first write the ordered pairs in a relation. Relation is less than equal to, so it means we can take the ordered pair as 2 is less than equal to 2, 4 is less than equal to 4, 7 is less than equal to 7, then 2 is less than equal to 4, 2 is less than equal to 7, and the last is 4 is less than equal to 7. Now construct its directed graph. For directed graph, first step is always take the elements from the set A. So there are three elements, so that is represented here. Label them, that would be a 2, this is 4 and this is 7. Now the first ordered pair in the relation is 2, 2. It means that is represented by the self loop. Here 4 is related with 4 again by the self loop. 7 is related with 7 again represented by the self loop. Now 2 is related with 4. Then 2 is related with 7. And last is 4 is related with 7. From here, we need to draw the hash diagram. Step number 1 is we need to remove the self loops and we need to remove the transitive edge. So after removing the self loops and finding the transitive edge, 2 is related with 4, 4 is related with 7, it means we need to remove this transitive edge. Now go to the step number 3. We need to put these elements in an upward direction. As 2 is related with 4, it means the placing of 2 is at the bottom as compared to the 4 and remove the direction. Next edge we have 4 to 7, means 4 is related with 7. So the placing of the 7 will be higher to the 4 and remove this direction. And this is the final hash diagram in this case. Now let's have a look on the shortcut how to construct the hash diagram directly without constructing the directed graph. So here we have taken the three different examples as a poset. We need to draw the hash diagram without constructing its directed graph. How to do that? Let's take the first case. In the first case, we have these elements and the relation is divide. Pick the first two elements. Check whether 1 divides 2 or 2 divides 1. In this case, 1 divides 2 but 2 doesn't divide 1. So it means 1 is related with 2. So place 1 at the bottom and the placing of 2 will be one level up to this one. So let's place 2 here and join them because 1 divides 2. Do not put direction in this case. Then take the element 3. Check whether 2 divides 3. No. Now check whether 1 divides 3. Yes. It means the level of the element 3 will be 1 above to the level of 1. Also, the level of 3 will be same as the level of 2. You can think like this. This is at the grounded level. Now 2 and 3 both at the first level, but there is no relation between 2 and 3. Means 2 does not divide 3 as well as 3 doesn't divide 2. Now pick the next element 4. So whether 2 divides 4? Yes. It means the level of 4 will be 1 above to the 2. Now whether 3 divides 4? No. 1 divides 4? Yes. But do not join directly. We just need to check from 1 can we reach to the 4 with any path? Yes. We can reach from 1 to 2, then 2 to 4. It means we have removed the transitive edge in this case. Pick the next element, that is 6. Now 4 divides 6? No. Then come back to the level because right now we are at the second floor. Now whether 2 divides 6? Yes. It means the level of 6 will be above to the 2 but at the same level of 4. And join them because 2 divides 6. Now whether 3 divides 6? Yes. So join them. 1 divides 6? Yes. But do not directly join them because there are two ways to reach at 6 from 1. Next element is 8. Whether 4 divides 8? Yes. It means the level of 8 is above to the 4. Now whether 6 divides 8? No. Whether 3 divides 8? No. 2 divides 8? Yes. But there is already one path to reach at 8. 1 divides 8? Yes. But there is a path to reach at 8. So do not join them. What about the 12? Now whether 8 divides 12? No. 4 divides 12? Yes. It means the level of 12 is greater than to the 4 level. Now check whether 6 divides 12? Yes. Do we need to join 2 and 12? No, because there are two ways to reach at 12. Even there is no need to join 3 and 1 with 12. This is the final hash diagram for the case 1. Similarly, construct the hash diagram for the case number 2. So in this case, the relation is divide. Again, we need to work with the divide relation. Whether 1 divides 2? Yes. It means the placing of 1 is at the bottom and the level of 2 is 1 above to the 1. 3. Now 2 divides 3? No. 1 divides 3? Yes. So its level is 1 above to this one. Whether 3 divides 4? No. 2 divides 4? Yes. So its level is 1 above to this. Whether 4 divides 6? No. Whether 2 divides 6? Yes. It means the 6th level is at the second floor and we have joined 2 with 6, as well as we are going to join 3 with 6, because 3 divides 6. 18. Whether 6 divides 18? Yes. It means the level of 18 is 1 above to the 6. Whether 4 divides 18? No. Whether 2 divides 18? Yes. Do not directly join them. Check whether we have any way to reach at 18 in the upward direction. Yes. So we can move 2 to 6, then 6 to 18. Take the next number, 36. So 18 divides 36? Yes. So it means the level of 36 is 1 above to 18. Now there is no need to join 2 and 3, 6 with 36, because there is a way to reach at 36. What about the 4? Whether 4 divides 36? Yes. Now whether there is any way to reach at 36 in the upward direction? No. We need to first come back, and if we are coming back, it means 4 divides 2, and that is incorrect. So it means there is no direct way to reach at 36 from 4. So me create that. So ultimately we have last option, that is we need to create that. Next we have 39. Whether 36 divides 39? No. Whether 18 divides 39? No. 6 divides 39? No. 4 divides 39? No. 2 divides 39? No. 3 divides 39? Yes. So its level is 1 above to this one. So do not think that if the number is greater than the level of that number is always upside as compared to the others. So here we have the final diagram for the case number B. Now taking the next case, we have power set with the subset where S contains the 3 elements A, B, C. So firstly we need to write what are the values in a power set S. So that is 5, singleton set A, singleton set B, singleton set C. Then we can take ordered pair AB, AC, BC, and then ABC. Power set means collection of all the subsets possible for this set. Now we need to draw its hash diagram. So phi is a subset of all the sets. So place it at the bottom. Now phi is a subset of A, but A is not the subset of phi. So we will place A above to the phi. Now B set. Whether A is a subset of B? No. Whether B is a subset of A? No. Now think for the phi. Whether phi is a subset of B? Yes. So we will place the B set above to the phi. Next set has C element. Whether A, B are the subset of C? No. Whether C is a subset of any of these two sets? No. Now think for the phi. Whether phi is a subset of C? Yes. So place it one level above. Now think for the AB. We have these sets in the level 1. Think for this whether this is a subset of AB. Yes. It means the level of this set is above to this. Now any one out of these is a subset of this set. Yes, that is B as well as phi. But we will not join phi because there is a way to reach at this point from here. Take the next element, that is set AC. So A is a subset of AC. So level of this set is above to this one. Let it be a here. Now whether C is a subset of this? Yes. Now whether B is a subset of this? No. Phi is a subset of this? Yes. But we will not join them because there is a way to reach at this point from this. Next set we have containing two elements B and C. So C is a subset of set B and C. Even B is a subset of this. So we will join them. And the last element we have in this set as set A, B, C. Now whether this is a subset of this? Yes. It means the level of this one will be one higher to this. So let's suppose it is placed here. Now AB is a subset of this. AC is also subset of this. BC is also a subset of this. So this is the final hash diagram we are getting in this case. In Poset, we have main four definition, that is a maximal element, minimal element, greatest element and least element. So one by one we will cover this one. Basically, an element in a poset is called as a maximal if it is not less than any element of the poset. In general way, we can say that X element is called as a maximal of the poset if there exists no Y such that Y is greater than X. So basically here the sign is not for the greater than, it is related to the relation. Means there exists no Y such that X is related to Y. If we have such scenario, then we can call X as a maximal. Whereas minimal means element in a poset is a minimal if it is not greater than any element of the poset. Means X is called as a minimal if there exists no element from the set such that Y is less than X. Sometimes there is an element in a poset that is greater than every other element, that is called as the greatest element. So we call X as a greatest element of the poset if Y is always less than equal to X for all values of Y in a set S. Means X is greater than each and every value of the set elements. Likewise, there is an element that is called as a least element if it is less than all other elements. Generally, we can say that X is a least element if X is less than equal to all the elements of the set. Also note that the greatest element and the least elements are always unique whenever they exist. Now the point is how to predict maximal, minimal, greatest and the least element if we have this set. It is very easy to predict with the help of hash diagram. Like in the previous case, minimal elements are always placed below. So in this case, 1 is called as the minimal element. Now what is the maximal element? Maximal element is not only 12, maximal element is 8 as well. How? Maximal element means if it is not less than any element of the poset. Right now, there exists no other element that is higher to the 8. It means it is at the highest position as per this route, or we can call it as it is the last destination of the route. So this will be a maximal. Moreover, 12 is a maximal because that is the last element of the route. In this case, minimal is starting point is 1, so we will call it as a minimal element. Now end of the roots are what? That is 39 and 36. So they both are maximal elements. In this case, starting point is 5, so it is a minimal point. And the end point is here. Each and every path end at here, so it is a maximal point. After calculating minimal and a maximal, we can count the greatest and the least element in a poset. How? If the minimal element is unique, that is called as least element as well. If the maximal element is unique, then that point is called as the greatest. For right now, both are acting as a maximal. It means in this case, greatest element does not exist. Whereas in the case number 2, least element is 1 because the minimal element is unique, so we can call it as a least one. And here again we are getting a 2 maximal elements. It means greatest element does not exist. In this case, minimal is unique, maximal is unique, so we call it as a least element, and this is as the greatest element. Let's practice more on these three diagrams. This is the hash diagram given to you. We need to find these four elements as per these three diagrams. In the first case, the minimal elements are A and B, and the maximal elements F and E. Least element in this case doesn't exist. Even the greatest element doesn't exist because they are not unique. In the case number 2, minimal elements are x1, x2, x3, and the maximal element is x7. It means least doesn't exist but greatest exists, that is the x7. In the next case, minimal element, there exists no element that is less than these one, so it means all acts as the minimal. There exists no element that is above to them, it means they act as the maximal as well. Both are not unique means least and the greatest element doesn't exist. So this is very easy to identify the element if we know how to construct the hash diagram for the poset.